So thank you very much for inviting me to this talk, to this conference. And it's a pleasure to see some old friends again, and even my ex-PhD student, Prasanna, who advertises in the audience here and is looking for a job, possibly in India, so clear at the beginning. Although he wasn't involved directly in this work. Okay, so I'm obsessed with singularities. I think they're typically, the most dramatic thing if you have something that blows up, and so they're worth understanding. And it turns out that they turn out to be universal things, and that's part of the philosophy of this talk. So an example of this that you might all be familiar with is phase transitions, which in principle are very complicated, except they're not. They're rather simple in some ways because you have scaling exponents and things behave in a universal way, and they're singularities as well. So I'm showing this particular picture here because it has singularities. Okay, this is a picture I recently saw in an exhibition in London, but these things on the bottom of the swimming pool here are called caustics, and they are focusing of light by the water waves, sunlight in this case, by the water waves. And you might think this is somehow random, but in fact, there is universality in the structures you get and the way that they annihilate and are created on the bottom of the swimming pool. And there's a very general theory underlying these singularities, which we'll get into. The specific topic of this talk then is singularities and decoherence. So the idea is basically that the quantum mechanics resolves many singularities of the classical world. The one I will focus on is perhaps the simplest, which are caustics. But there are some, basically the whole of quantum mechanics kicked off with the ultraviolet catastrophe, which is solved by quantizing the electromagnetic field, for example. Singularities in cosmology and so on are extremely important, and the hope is, it's of course an ongoing story, but that these things will probably be smoothed out by quantum effects. But then here comes the thing. So with decoherence, we go back to the classical world. Okay? And so then the question arises, what happens to these singularities? Okay, are they reintroduced? You get a paradox that the singularities you initially removed by quantizing somehow get reintroduced. So what I'm going to do is give you a bit of background into singularities, and I think the easiest way to see that is in terms of optics, but as I will explain, it goes further than that, and that'll be a sort of, in a nutshell, description of caustics and catastrophes. And then I'm going to look at how those singularities are resolved by going basically to first quantization, by talking about waves, classical waves. But then we're going to look at then a new generation of catastrophes that I call quantum catastrophes. And those are catastrophes that exist even in the classical field theory, and you must second quantize to remove them. And those are the ones that are going to be particularly susceptible to decoherence as a quantum effect. And so we're going to then see finally what decoherence does do to a quantum catastrophe by looking at a weak measurement, a weak continuous measurement. Okay, so here's a gallery of some pictures of caustics. Who has seen this before? 1, 2, 3. Call yourself physicists. You should be looking at things in nature and wondering why they occur. Okay. Oh, you saw the girl immediately. So that is Michael Berry's daughter, actually, in a swimming pool a few years ago. Yeah, so this one is one that we see in everyday. This is also one every day, and that's the point, that these are things that occur in everyday sort of experiences. It turns out that caustics are very important in trying to understand gravitational lensing and tracing back to try and figure out what the mass distribution is in the universe, dark mass that you can't see directly with light. But nevertheless, it bends light. And rogue waves, of course, another important thing. Something that's come up a little bit in this conference is Anderson localization, and it turns out right at the transition, if you look at the behavior of the wave packet, it takes on one of the classic caustic forms that I'll get to. All right, so how does this work? Well, the idea is that if you have a cup and then you have rays coming from above, from the sunlight, then they reflect off the back wall of this. If this was a perfect lens, so this was parabolic, they would focus perfectly at a point. But it's not, it's circular, so they don't. And generically, they form this cusp structure. This cusp point is what remains of the original focus if you move from a parabolic lens to a circular one, but then you get these, what are called fold lines. And this is then, if this was a plastic cup, and I could put my hand and distort it slightly, the point is that these things are structurally stable, so they'll get twisted and sheared and deformed, but they maintain their same qualitative shape. And they're generic, in other words, and that's why they occur all over the place in nature. Another key thing you need to know is that if you look in the geometric theory of light here with these rays, the light intensity diverges along this caustic line. So it's a failure of the geometric theory. Here's another example. So this is called the Hamiltonian mean field model. It's the XY model, basically, with a long-range interaction, a very long-range interaction, just the same infinite range interaction. But you can also think of this as particles on a ring. If you started with them all equally distributed around the ring, nothing would happen. But if you introduce just very slight perturbations from being equally separated, so that's what's shown, this is the density distribution as a function of angle, and you let the system go, you find that they spontaneously focus. And what do you know? You get these cusp structures. This model was introduced to study long-range interactions in statistical mechanics of long-range interactions as a toy model for gravity, believe it or not, and it shows some similar features to gravity. This is called violent relaxation. And the system persists. It seems like it started off very close to equilibrium, but these excitations persist for incredibly long times. The system really doesn't relax, except in incredibly, it's a non-integrable model, by the way, but it really takes an incredible long time to relax. Caustics are also supposed to lie behind the large-scale structure of the universe. So if you start off with mass distributions generically and you let them fall under gravity, then you tend to form singularities. And this was realized very early on. Okay, so the incredible thing is that not just any sort of singularity can appear in nature and be structurally stable. Of course, if you tune the conditions, you can get a focus point if you want. But generically, if you don't have any special symmetries, then structurally stable singularities can only take certain forms. And these are the first few of them, and they're described by catastrophe theory. So in one dimension, the structurally stable singularity is just a point. In 2 dimensions, it's this cusp. And in 3 dimensions, you get these 3 possible objects. They each form sort of universality classes, for instance, these 3 guys in 3 dimensions. So they can't be smoothly deformed from one to the other. So this is a very strong statement that structurally stable singularities can only take certain shapes. And there's a mathematical way of expressing the same thing. And if we think in terms now of mechanics, then what it says is that the actions can only take close to one of these singularities, the actions take one of these forms. What they are polynomials in some variable s, which somehow labels the paths. I'll be a bit more specific in a second. But they are linear in the control parameters. So if I go back one slide, the control parameters are the dimensions. They're the things you can control, and you can use them to what's called unfold the singularity. The most singular part is at the origin. But these control parameters are things you can use to unfold this singularity. And how general is this? Well, these are the singularities of gradient maps. And that's a very general thing, because anything that obeys a variational principle turns out to be a gradient map. Fermat's principle, for example. Yeah. Yes, S labels the possible path. Yeah. it would label where they entered the cup, or where they bounced off the back wall, where they reflected off the back wall, for example. Well, maybe it'll be clear if I show you an example that I'm coming to right now. Okay, so for example, if we have this quadratic one, which is called the cusp, sorry, not quadratic, quartic one, it's quartic in S. So according to Fermat's principle, to find the allowed classical paths, we should find something that's stationary with respect to variations in the paths. So we do this and we get something that's cubic. I'm now going to plot that as this surface above the control plane, which is in this case two-dimensional C1 and C2. Okay, so this gives you, so for instance, if you're over here, you just get one solution, and if you're over here, you only get one solution. But inside this cusp-shaped region, there's three solutions. For every C1 and C2, every point here, there's three possible classical paths reaching that point. Now, the caustic condition is to go one, is to look for where the action is stationary to the next highest order. So that's a sort of focusing. It's where many rays go to the same point. And that picks out exactly where the surface turns over. And it's these, again, gives these white lines in this bottom plane. And so if you eliminate now from these two equations, S, you get an equation for a cusp in this plane. Okay, so in fact, these numbers here are not universal. So 4 and 2, I've just put in for convenience. It can be anything. So, of course, in nature, you get some generic structure, and you can map it onto. So each of these catastrophes form a class of, and so if we go back, the idea is that each of these guys, let's say we looked at these three ones here in 3 dimensions, each of these form a class, but I can play around with the numbers that appear in front of them. I'm free to do that, as long as any transformation which is a diffeomorphism. So any smooth transformation, anything I can do with a rubber sheet, but without cutting it, is allowed. And then you say it's really the same object. Yeah, so here in these higher ones, I'm allowed to introduce more variables parameterizing the paths. So this was all for, this looks very classical in some sense. But we know how to go from classical to quantum, for instance, doing a path integral. If we know the action, okay, we know how to go to the quantum. And so it turns out that, well, that's what we do. We just put each of these universal actions. Now we integrate, so you can see this is, you can sort of think of this as a path integral because we're integrating over the variable that labels the path. And the first one of these is very old and well known. It's the area function. And it turns out this is the wave that universally dresses what's called a fold. So in one dimension, a singularity will universally be dressed by an area function. Of course, in any physical situation, there's some mapping where you may stretch it and do all sorts of things. In 2 dimensions, well, that took about another 100 years, but it's called the Pearcey function. And you can see here then it's this quartic guy, and this is the universal wave function that dresses a cusp, so something that occurs in 2 dimensions. And now, so this is the sort of the geometric version, the black line, but now you see you get this interference pattern around it. If you look at the phase, something very nice happens, and that you get these pairs of the vortex-anti-vortex pairs. Each of these is a vortex-anti-vortex pair. And outside, you get a line of vortices. So this is a sort of morphology that you get in the wave theory around a singularity. And so the point is that these singularities then are removed by interference. Oh, and I should say, so people cottoned on at this point. It took 100 years for the first 2 of these, and then people said, okay, maybe there's a whole hierarchy of these things. And so there is, and it's in the last chapter in this book here, the latest version of what I think of Abramovitz and Stegun has been updated, and it's now the NIST Handbook of Mathematical Functions. It's all online. It's the digital library of mathematical functions, and you'll find these things in the last chapter in there. So there's a hierarchy of these things. And just to emphasize very quickly, one very nice property of them is they have scaling features. So you can think of it as you change, in this case, the wavelength or the wave number, then they're self-similar and they rescale, and you wind up changing the coordinates, basically, the control parameters. And you have these exponents here, which are called Berry indices, and there's a whole sort of hierarchy of these indices that go with this hierarchy. And they also become more and more singular, let's say, as you change the wave number and make it very short. What you find is that all this structure, as you reduce the wavelength, all this structure gets pulled in towards the most singular point, and it all speeds up, as a function of distance, as a function of the control plane, which is this plane here, all the oscillations happen faster and faster, of course, as the wavelength gets reduced. And so they obey these self-similar things. Okay, so then, where I want, that's sort of my departure point, because now I want to ask questions, are the places where even this wave theory, are the types of singularity that even this wave theory doesn't deal with very well, and you need to go to the next stage, which is effectively second quantize your classical wave. And so one example of this was given by Ulf Leonhardt, and he thought of the case of a classical wave propagating over an event horizon. So it turns out that if you look at the phase of this classical wave, it speeds up, and that this is basically gravitational redshift in reverse. As you get close to the event horizon, your wavelength gets shorter and shorter and shorter. It goes as basically 1 over the distance from the event horizon, your wave number. So the wavelength becomes, at the event horizon, your phase of your wave is oscillating infinitely fast, and it turns out you get a logarithmic phase singularity. And so the idea is that classical theories don't do very well near event horizons, and the way nature solves this is, well, firstly, there's no real such phase becomes ambiguous in quantum mechanics. There's no such thing as an emission phase operator. And so the way nature gets around it is by producing Hawking radiation. So it's a very interesting paper. Michael Berry has explanations for this. In fact, he describes this as one of his 3 obsessions in life. One of the others is the zeros of the Riemann zeta function and things like that, and trying to describe that with quantum chaos. But this is also on that list. And so then I have a theory on this which is much more mundane, but okay, it's a low energy thing, and it's really in Bose condensates, and I'm going to describe that now. And it turns out that the natural place for these singularities of classical waves is in Fock space, which is sort of maybe the natural arena of a quantum field theory. But I'm going to proceed with an extremely simple example, and I will stick with this through the talk. And this is the 2-mode quantum field, okay, the simplest, well, simplest non-trivial field, let's say. And it has, so we have two operators, A and B, 2 annihilation operators that annihilate excitations in these 2 fields, and I'm going to think of bosons. And now you can, so this came up actually, and Stefan's mentioned this model in his lecture this morning, that you can map this onto a giant spin, whose length is so I'm always going to think of some 2 fields that are coupled, but I'm going to conserve the total number of excitations. So we're talking low energy systems now, so that I can swap, let's say, the particles, the excitations between the 2 modes, but the total number will be conserved. Then using this Jordan-Schwinger mapping, you can map this to an SU2 model. In other words, the Poincaré sphere, where we have some giant, I should have really drawn a big arrow going from the origin out to here, which is some giant spin made up of all these elementary spin 2s. It's a spin 2 system because it can really live, it can live in one mode or the other. So examples of this would be 2 coupled Bose condensates, and these have been made in a whole host of experiments. So the idea is that the particles can hop from one side to the other. I'm also going to put in, it's going to be important for this, interaction. So they're going to interact with each other when they're in each condensate. You can do this as, so this is like a Josephson junction, in fact, And but you can have the so-called internal one where you do it where in fact the atoms occupy a single external mode, but now you have internal states. And you drive the tunneling between the two states is now an internal drive between internal states of the atoms. You can control that with a laser. Okay, and what we're going to add to this eventually, slowly getting there, is a continuous measurement of the number difference. So you can shine a laser on this and do absorption imaging, and you can count. You need to resolve these two clouds, but you then count. You can do it in situ, and you can count the number of atoms in one and count the number of atoms in the other, and then you can measure the number difference. And the idea is we're going to do that continuously, but very weakly. So we don't destroy the system, but very weakly read out the number difference between the two. Yeah, you could do this with photons. I mean, I don't know how, but in principle, you could have an optical Josephson junction. There is a few papers on how to realize that. Is that what you mean? Yeah. People have thought about how to try and do this optically. So the model we will use for our sort of quantum model that we'll need to use to get the, so the classical model for this would be the Gross-Patevsky equation. That would be our classical field theory. And our quantum field theory here will be the Bose-Hubbard model. And so this describes hopping between sites, and this is on-site interactions here. And we're going to reduce this, in principle, complicated model to just two sites, a left site and a right site. So I'll always think in this model of spatially two modes. And then this model reduces to the hopping term, and then the interactions reduce to the square of the difference between the left and the right mode, plus some constant terms. So just a few lines of algebra to go from there to there. This is what it comes to. And in more standard Josephson junction language, the constant you put in front here would be the Josephson tunneling, EJ, and then you have what's called the charging energy, EC, except here everything's neutral, but it comes about from the interactions of the particles, so it depends on the scattering length of the atoms. Now, we can write this in, using this Jordan-Schwinger transformation, we can write this in spin language. And so the interactions give this nonlinear term. So SZ is the difference in the number of excitations between the two condensates. So our distance up and down, our vertical axis, up here they're all on one side, and down here they're all on the other side. Okay, so that's our SZ. And our SX gives us the coherence, basically, between the two sides. But it comes about from the hopping term. So we define these macroscopic operators as just the sum of all these spin halves where the particles live on the left or the right. Okay, and another example of this exactly the same Hamiltonian would be the Ising model, but with infinite range interactions. It gives exactly the same thing. This is also known in nuclear physics as the Lipkin-Meshkov-Glick model. And I'm not sure if, I know Krishnendu Sengupta isn't here, but I'm not sure if any of the authors of this paper are in the audience here. Not today. But it's known, this has been studied in India. So, if you look at the classical limit, then we can describe this system. So formally, you can take this Hamiltonian and reduce these operators, replace them by complex numbers that commute, and you come to this Hamiltonian here. So now little n is just like SZ, it's the number difference. So I'm going to flip between different notations a little bit because this is the notation that tends to be used in this field. This is the number difference, and then phi is the phase difference, and that's the azimuthal angle around this Bloch sphere. And this looks somewhat like a pendulum Hamiltonian, where this is the angular momentum of the pendulum, n would be the angular momentum, and phi is the angle away from pointing straight down, the sort of ground state, if you like. But there's this extra term in here, which means which depends on the angular momentum in front of the potential term. So that makes it look like it's a pendulum with an angular momentum dependent length. And then so if you take Hamilton's equations, you get actually Josephson's equations in this case. maybe slightly generalized from what you're used to seeing before because of this square root term. And these are the classical, these, if you like, are my classical equations of motion. Phi and n at every moment have perfectly defined values in my classical theory. And so you get various motion on the Bloch sphere. So here you can see some Josephson oscillations going backwards and forwards between, in fact, plasma oscillations going between the, you start the system off mainly in one well, and then you let it go, and it gradually oscillates between the two wells. And this isn't just single particle tunneling, it's going about 10 times faster because of the interactions. They drive, because of the nonlinearity, they drive this faster. You can also get what's called self-trapping, which is less glamorously called Josephson AC oscillations, where if you start with enough number difference between the two sides, it sticks there, and it's unable to tunnel. So you can get this classical motion. And now I'm going to think of a very particular initial condition, a rather quantum one. So I'm going to take two condensates that have never seen each other, and I'm going to suddenly put them together. Okay, they have no initial phase relation between them. Well, then, the proper thing to do, this is actually a rather quantum thing. So each of these lines I'm showing here, this is the phase as a function of time, or the number difference as a function of time. So solving the Josephson equations for a particular initial condition would give me one of these lines. But that's not really the right thing to do in this problem, a single classical trajectory. We want to do something more like what's called the truncated Wigner approximation, because the idea is that quantum mechanically, number and phase obey some sort of commutation relation, at least semi-classically. And so if you start off with two condensates that have never seen each other before, you start off with well-defined number difference, but no phase relation. And that means really your initial condition should be described as an ensemble of all possible initial phases. So that's what's shown here, an equal distribution of all possible phases. You let the system go, what happens? Well, what do you know? You get back these Cusp caustics, again, following this quench. Why? Well, because catastrophe theory basically tells us if you're going to get a singularity, who knows, you may not, but if you do, then the structurally stable, the generic ones you're going to get in a two-dimensional control space, let's say phase as a function of time, or it could be number difference as a function of time, will be cusps. And that's what you get. If you now look at the quantum story, so underneath now is the classical story. If you look at the quantum story from solving the this Bose-Hubbard model, then you get interference patterns, and we get back, in fact, this Pearcey function is dressing each of these guys. Okay, each of these cusps, and formally you can also think of these as revivals of the initial wave function, not perfectly revived, but close. So what is really happening is you start in with a quantum rotor. This is your energy spectrum initially before with two separate condensates, and you move now to this sort of quantum pendulum Hamiltonian, and you change the energy spectrum. You introduce basically a gap in the bottom of the spectrum, but there's also something called, you get a divergence of states around the separatrix here. This energy here is the difference between a pendulum that can just reach the top or can go over the top. So these are states that are windmilling left or right. They're doubly degenerate whether you're going left or right. And so people refer to this point as a dynamical phase transition. Above and below, you get two very different types of motion. And you get a sort of a peak in the density of states at this energy here. Okay, so why was this a catastrophe? Well, we got the nice cusp shape, but formally, if I did this with the Gross-Patevsky theory or this classical theory here, with these trajectories, and I add up the trajectories arriving, let's say, at this end point, I run the experiment for some time, and I just bin the trajectories, then this is what I get. So at some end time here, I get these singularities. These are 1 upon square root singularities in the classical field theory, in the Josephson equations. So my classical field theory is breaking down at this point. So this is why I call this a quantum catastrophe. But when you go to the Bose-Hubbard model, it discretizes my system, and now it's smooth is not the right word. It removes my singularities. It regularizes them. So I'm regularized by introducing second quantization, by discretizing my excitations. And this is my version of a quantum catastrophe, and it's very, of course, it's closely connected to catastrophe theory. I should say, local plug, this is very closely connected to work done. You get similar structures when you look basically at the diffraction of light by ultrasound, which was work done by Raman and his student Nath back in the 1930s. And when they look at the diffraction pattern of light from a standing wave of light, they get these discrete lines which obey something called the Raman-Nath equation, which is basically the Mathieu equation in Fourier space, and that's very similar, apart from my square root term in my classical Hamiltonian is a very similar equation. Okay, so I should say that these things also come up, just a brief sort of plug, of light cones as catastrophes, where you do some sudden change, some local change in some spin, you flip some spin, and you find that they get these structures. These authors didn't identify them as so much as such, but I would call them, I mean, that they're quantum catastrophes, that we have related work where we show that these things are actually one of these catastrophe functions. In fact, well, okay, here it is. This is looking at a local quench in the transverse field Ising model. You get this light cone, but actually what this is two back-to-back Airy functions propagating out. But I won't say more about that, because I want to get on to, in the last few minutes, the weak continuous measurement. So the idea is now we add in, so this is our master equation. This is the Hamiltonian part here, with the sz squared term and the sx term. But now we add in this triple commutator, which is a double commutator, but it gives, you might not be used to seeing in that form, but it's exactly the Lindblad form of the master equation. And we're measuring here, what are we measuring? Sz, it's the number difference between the two condensates. We do it with a strength d. Here, lambda are parameters that exist in the closed system, and they just give the ratio basically of the interaction energy to the tunneling energy. And so what do you get when you do this? So this is our classical theory with no decoherence, but we might expect to be reduced back to this theory when we, wow, this is flashing at me. Very high tech. We might be expected to be reduced back to this theory when we add decoherence. This is our quantum theory with no decoherence, so we get these nice, it's regularized by the discretization in Fock space. This is the number difference plotted down here, function of time. Now, when we add decoherence, we find, so the question is, I said these catastrophes are structurally stable. They're structurally stable singularities of gradient maps. Although it's far from obvious that the master equation is a gradient map, and in fact, I don't think it is, but I'd be very happy if someone has any insight on that as to whether it can be really described as a variational principle. So it wasn't clear to me a priori what would happen to these catastrophes, but I guess it's intuitive. You imagine if you do it weakly, they survive, and indeed they survive, but they gradually get washed out. Okay, so we don't see any singularity. We don't seem to be heading back to this picture at all. We get a smoothing out, and at long times, you just get an equal distribution. You get the high to infinite temperature limit, where equal probability of all number differences, and that's what's described here. I can be a bit more quantitative than that. So if we look, so this is our quantum theory. I haven't drawn it discrete. I've sort of joined the dots here to make a sort of continuous curve. You see the interference oscillations. You see the classical catastrophe. This is without any decoherence for 400 particles in the quantum case. The classical case is effectively infinite number of particles, infinite number limit. If we vary the measurement strength, so now we put d being non-zero, we put in some measurement, we find that we wash out the oscillation. So we begin to return towards this classical theory. The red line is for kind of strong measurement. The blue line is actually for, sorry, opposite way around. The red is for a rather weak measurement, and the blue is for a stronger measurement with time. You see, we begin to return back to our classical theory, our classical singularities. But, and if you vary number, where you can see if the number's high, you're closer to a classical theory. If your number's lower, you're not so close to the classical theory. So the paradox, if it ever was, which it really wasn't if you thought about it, is resolved in the, basically what is happening is, although we are washing out interference, the effect of our bath is also to put in quantum, is also to put in noise. And in fact, we could map this master equation onto a Fokker-Planck equation, then we get a diffusion term, which is also going to spread out any of our singularities. And so here, if you look at the effect, if you look at the widths of these caustics, what you find is, as you vary d, the measurement strength, you find that the width actually, that they get widened as you increase the measurement strength. And so you don't get returned to a singularity at all. And if you vary the number of particles, well, if you increase the particles, you can return towards a classical theory, but there's no paradox there. The paradox would have been if for a finite number of particles, a finite n, we return to a singularity. If we get a singularity for an infinite n, that's okay. As long as you put it you put in infinity, it doesn't matter if you get out infinity. But if you put it in a finite number, you got out infinity, that would be a problem. Okay, and so you could still achieve classicality, but you'd have to send n to infinity whilst doing the limit of a very weak measurement and keeping their product finite. Okay, so my summary is that these catastrophe things are generic in classical quantum dynamics. They're generic singularities, and in the simplest case we can think of, it's the cusp. There's higher order ones, and I've looked at some of the higher order ones, but I didn't have time to go into that. There seem to be 3 levels of structure, at least. There's a sort of geometric theory. This is smoothed out by a classical wave theory, but then there are these quantum things when you get singularities of the classical waves, when you do more exotic things. And in particular, quantum catastrophe is one that's regularized by discreteness of the field. So you have quanta. A continuous measurement difference will kill the interference in general, but it also adds noise. So that gets rid of any possibility of singularities. But in principle, we can still reach the classical limit if we send n to infinity and we keep the measurement extremely weak, but that's no paradox. Okay, so thanks for your attention.
So these continuous measurement case, the results you showed were all the master equation simulations, right?
Yes.
So what happens if you look at single trajectories, which are somehow also, and also you can unravel them into more than one unique single trajectory, so you could measure them. Yeah. So basically, what happens with the single trajectories?
I don't know. So even I can solve a first-order differential equation, which is what I succeeded in doing, but I haven't done the quantum trajectory method. But if you're interested, yeah, I don't have a statement to make. Indeed, the master equation is an ensemble average. And so it leaves open the possibility, yeah, although these are singularities in probability distributions, so I should be maybe clear, I don't believe there'd be any, even there's no obvious singularity in a single realization. So these are singularities in probability distribution. So I don't see there as being a problem in a single realization. Nevertheless, what happens in a quantum trajectory is still, I think, an interesting question.
So this might be a naive question, but in these Bose-Einstein condensates and some other systems, we find that we have shock waves, right? So would you call those singularities? The onset of shocks in these BECs, or would you call them? It seems that they are also similar singularities in density functions, right? So
yes. So I think in real space, you're not going to see a singularity in the Gross-Pitevsky equation. I don't know. It'd be interesting to put one in. You'll get solitons and vortices. Okay, so a vortex is an example of a singularity in that it's a phase singularity. So, right, the system takes all possible phases in the core, but the way nature deals with that is to put the amplitude to 0. So these are studied a lot in optics, where they're called optical dislocations, and they have a whole morphology that people have studied. They can be resolved by adding in polarization. You always resolve these singularities by adding another degree of freedom in. So in the case of the shock wave, as it were, as in the light cone experiments, then yes, I think these are catastrophes, but there they are, well, they're resolved in various ways. So in real space, I think everything would be smooth. When in the pictures I showed on the lattice, then it's naturally discretized actually in real space, and so there you automatically sort of get a quantum catastrophe.
I mean, typically they are resolved by some higher gradient terms or some terms in the theory, but the onset is what we sometimes call gradient catastrophe, right? There's a catastrophe in the gradient, and the gradient almost becomes infinite. And then higher derivative terms correct it, and you get these dispersive shock waves. But the onset, I would think that we can call this caustic.
You're talking about with the Gross-Pitevsky equation or hydrodynamics?
Right. In the Gross-Pitevsky equation, suppose you have the Gross-Pitevsky equation and write some hydrodynamic form in terms of densities and velocities, and then you sort of ignore the higher derivative term, then
the quantum pressure.
The quantum pressure. So then,
then yes. In the hydrodynamic formulation, you could get singularities.
And it's the same kind of singularities.
I have a strong feeling yes, because structurally stable singularities should be of one of these forms. It doesn't matter if it's a nonlinear theory or not. But I haven't checked, so that's a guess. You typically get airy functions around shock wave fronts.
You started with the situation that you had basically two decoupled condensate. Now let's imagine that we have some coupling initially and then we change the coupling.
Yeah.
Would one still see this kind of singularities?
Yes.
Yes, so that's universal.
Yeah, so we've looked at, so this was a very weird initial condition, and a very extreme one for simplicity, where we started, if you like, in Fock space. We started with a number difference, so this is number left minus number right. And we started with, and this is the probability, we started with everything in the zeroth mode, just for symmetry. But if you start off with a Gaussian, let's say, and you suddenly, which is the ground state when you have a little bit of tunneling, and you suddenly do a shock, it survives, yes. It's structurally stable, yeah. I should have maybe emphasized that.
Ising model?
Yeah, so the Ising model, I would say, is nonlinear.
Oh, you call nonlinear?
I would call it nonlinear. It's solvable, but it has interactions in it. You can map it onto free fermions, but it's nonlinear spin model with interactions. And yeah, so the key thing here is exactly that if these energy levels were quadratic, okay, so they were equally spaced, then you get perfect focusing and you wouldn't get a catastrophe. The point is, because it's nonlinear, these energy levels, in other words, if this was a perfect lens, this would be quadratic. So in the transverse field Ising model, you also get cosine things coming into the quasi-particle description. Your dispersion relation and so on is cosine, and that's why you get basically the same stuff coming out. So here, yeah, nonlinearity is important. But you can also set it up in the initial wave and then propagate it freely. That's kind of what happens in optics. And you get these catastrophes. The wave propagates through some medium and you get some complicated wavefront. But then you let it then propagate through free space or onto the bottom of a swimming pool or something, and then you get these structures forming. But as long as you have these initial structure built into the wavefront, it'll be maintained.
Any further questions? If not, let's thank Duncan.
Thank you.